What comes next in the article is the calculation of total precipitation. At the beginning of the video, we saw an Excel table containing several meteorological stations along with their x and y coordinates, monthly and yearly precipitation values, and at the end of the table, the average precipitation for each station between 2000 and 2025. This average value is what we'll be using next to specially represent precipitation across our study area. We'll start by converting this table into a shapefile using the x and y fields from the attribute table as the coordinate reference. So we just need to right-click in the total precipitation and select this create points from table, xy table to point. Here on the table to point, as the input table, this will be the total precipitation.csv. Output feature class, this will be saved also in the metadata. We can call it something like, let me think, TP. Let's click OK. So the X field will be the X and the Y field will be the Y, and the coordinate system in this case will be WGS 1984. Since many of these stations are located outside our study area, we can go to the environment settings and define that we only want to include the stations within our study area. To do this, we can set our study area layer as the mask or extent, in this case the DEM, ensuring that only the relevant points are used in the analysis. So here on the processing extent, in the third symbol, we can set the DEM as the extent. Okay? So now only the points inside the DEM will be processed. So let's click OK and see the result. So let me see and zoom to layer. I think something went wrong. Let me see why. Let me open the attribute table to see if something went wrong. Maybe I did something wrong in the processing. So let me see. So we have zero results. Let me remove this and do the process again. So let me just go to create points from table again. And sometimes I think I know why this happened. Maybe the X and Y field are wrong. I will try to use the Y field in the X field and the X field in the Y field and see if this works. Let me click OK and let's see now. Okay, now it automatically worked. So let me zoom in the points and open the attribute table as well. And let's see. Okay, we have 4 stations in our study area. So what we need to do in this example, and if you are following the video, you need to swap the X and Y field. Okay, so let me just add labels to see the yearly precipitation, the average of the yearly precipitation. Let me check this one and click apply. And we can see that we have the lower values near the coast, near the coastline, and the higher values more to the center of the, or to the east of the study area. So how can we use this information in GIS? We can use the IDW tool. So go to the geoprocessing tool and search for IDW. It's this one. Let me just drag and drop the shapefile of the stations into the input features. In this case, the z value field will be the total precipitation, the average of the total precipitation. Let me just save this in the mid data folder as well. We can call something like TP underscore IDW. As well, the cell size will be 25 meters. And we set the environments as well. And in this way, we have a spatial representation of total precipitation. Obviously, the more stations we have with data, the more reliable and accurate the result will be. Next, you already know what you need to do. We need to reclassify the IDW raster using the value ranges provided in this article. We can see already that the values are quite different. I mean, the highest value from the article is lower than my lowest value, so we need to do something to address this, which in fact isn't really a problem at all. It's just that we're dealing with different study areas and completely different datasets. To solve this, I'm going to use a simple reclassification method based on quantiles, dividing the data into 5 classes. So, clicking in Classify, I will change the method from manual interval to quantile. It's this one, and set the classes as 5. Let's just, okay, click OK. For the new values, we don't need to do anything, because if we go to the article once again, we can see that the lower total precipitation values will have a value of 1 and the higher values will be 5, which is what's happening here in this example. Okay. For the output raster, this will be saved in the results folder. So let's select the results folder. And we will call this R_TP for total precipitation. Click OK and set the environments, and then click Run again. So here we have the reclassified total precipitation data, and once again I'm going to adjust the symbology to better visualize the results. Now we can clearly see that what I said in the beginning of this step was true. The lower values are located more near to the coast, to the ocean, and the higher values are more located on the east side of the study area. Let's now move on to the effective precipitation. But first, it's important to understand what this is. If we do a quick search on Google, we can see that the effective precipitation is the amount of precipitation that is actually added and stored in the soil. It said also that during drier periods, less than 5 millimeters of daily rainfall will not be considered effective, as this amount of precipitation would likely evaporate from the surface before soaking into the ground. Effective precipitation enters the soil and becomes available to the plant. Effective precipitation is calculated based on an equation that requires both the total precipitation and the curve number values. I'm going to open the raster calculator tool, as you can see in the ArcGIS Pro, and explain the equation as we go. First, let's type float to tell raster calculator to return the final result as a floating point number, meaning it will preserve decimal values instead of rounding them. Next, we type power. This means we are going to raise something to a power. In this case, we're squaring a value, so the exponent will be 2. And next, since the original effective precipitation equation was developed using inches, we need to convert the units as we are working with millimeters. So inside the parentheses, we just type TP_IDW and we subtract with the value 5080 and divide by the CN raster. Just do it like you are seeing on the screen. Next, we close the parentheses and we do a sum with 50.80 and then close the parentheses again. To finish this part, we use a comma and then we do a 2. That will be the exponential value we talked earlier. Then we divide again, we open the parentheses again, 2 parentheses actually, we select the IDW again, and then we don't want to subtract, but we want to do a sum using this value and dividing by the curve number raster again. Then we close the parentheses and we do minus 203.2. I will try to remember to place this equation in the description below so you can use it. Let's save this in the MIDdata folder. We can call this EP, and let's change the environments, and then we need to reclassify. We're facing the same issue as before. The values are quite different from those in the article, so once again we'll use the quantile method to reclassify the data, okay? So let's open the reclassify tool once again, drag and drop the effective precipitation as the input raster, click on classify and choose the quantile using 5 classes. So the method will be quantile again, and the classes need to be 5. Once again, we don't need to change this the values, the class values in the reclassification because they are already sorted. We just need to set the output for this new raster. This will be actually the final result, so this will be saved on the final results folder, and we can call this r underscore EP. And let's click OK and set the environment one more time. Once again, let me just change the symbology to match the other results. And then we just need to set the floodplain as we... Thank you for watching. If you like this type of content, don't forget to like, subscribe and comment what you want to learn next.